So let's make a lie detector for the globe. And what the globe says, I'm interested for now in the first two things, that it's a ball and it rotates around its axis once every 24 hours or 15 degrees every hour. So the first step is, here's the ball and here's the rotational axis. The first thing is that we need to recreate a replicant for that axis. And the way to do it is, you look at your latitude line and you subtract it from 90 and you get an angle. That angle is the angle of the plate, the most important component of that device, on the horizon. That plate will have the rotational axis perpendicular to it. So when the Earth rotates, you just replicating the motion on that plate with any rotary or rotational parts. Of course this plate must be pointed to north if you are in the northern hemisphere. Uh, so now we mentioned two angles. The orientation is north, and the angle of the plate, which is dependent on your latitude line. And then the third angle is, as you see, that ray of light of the sun uh, coming down. Of course, this is winter in the northern hemisphere. This triangle is very important, and we need a piece of information. This small angle at the tip of the triangle, we get it by knowing where is the sun perpendicular on the earth on that day. Or you can just simply look at time and date and get the elevation angle of the sun during zenith, and that angle you subtract from it the angle of the plate. So now you have the yellow triangle of that. I will call it green triangle because it will come later as green. I made the device and I started tracking the sun along the day 2 or 3 times. The accuracy was okay. Of course, as you see, it's just made of wood, something made at home, and a little bit loose. So the results were satisfying for Globehead, but I knew it wouldn't be satisfying for someone skeptic. So I had to put the device into tests to test it mathematically, or in other word, more of trigonometry. And before you say math and trigonometry can lie, no, it doesn't. It only gives wrong information when you put wrong input, or put irrelevant equations to get something that you want. Uh, the the way I made this test is explained in another video. You can see some lines here: purple, black, and blue and red. So I recommend you watch that video before continuing. So the most significant things that I noticed in that device, even before I tested, is during sunset and sunrise, the upper tip of that green triangle is horizontal when you are looking from front view, and when you look from top view, uh, you find it that it's pointing a little bit towards the south, since the plate is oriented north. So we can get the angle of the sunrise and the sunset. And if you look at the plate perpendicular to the plate, you can see that on the left will be 6 a.m. On the top side should be 12 p.m. and on the right side 6 p.m. This is a 24 hours dial. Uh, so we can see where is the shadow, or the light of beam is pointing when you are looking perpendicular on the plate, and you make an angle between the 6 a.m. and the green triangle, and that angle, if you divide it by 15, then you get how many hours after 6 a.m. Uh, you get the sunrise. So that's basically how I started testing the device. It's that moment of sunrise and sunset. If I can solve the triangles and get uh, the angle of sunrise and sunset and the length of day to test the integrity of my device, then the device is working, and any lack of accuracy is due to uh, bad manufacturing. So it did give the results as expected when I compared with time and date and SunCalc, uh, with say like 1 or 2 degrees sometimes of error, and maybe up to 5 or 15 minutes for day length, uh, and I'll come to that later. But anyway, I still didn't like the fact that I have to go to time and date to get the third piece of information, which is the elevation angle of the sun during zenith. I wanted to uh, calculate it on my own, and since I had some practice with the testing the first and the second aspects of the globe as mentioned above, I started to solve more triangles to get the elevation angle of the sun on the earth at any time of the year. And of course it's not accurate, of course, because I'm not an astronomer. I don't have any scientific degree more than high school. I didn't study astronomy or anything like that, so I made my calculations upon the Earth going in a perfect circle orbit around the Earth, which is not the case. So the elevation angles goes off by somewhere between 0.1 and 0.9 degrees when I compare it to time and date. And this results in itself, it solves the third and the fourth aspect as mentioned earlier. So I made all of this into an application that gives me 6 pieces of information. The elevation of the sun during zenith, the length of day, sunrise and sunset angles, and other piece of information is the azimuth of the sun at any given time on the day, and the elevation angle also at any given time on the specific day. I have this this part of in the application or the spreadsheet on the top right corner. As you see, it's the refraction factor, and if you just put a 0, then you get the information without refraction. And if you like to get more accurate, then you put the 0.83 degrees angle, and this angle means that when the sun is below the horizon by 0.5 degree, something like that, then the upper tip of the sun is still visible to you. So that angle, in fact, 0.83 is 1.5 sun diameter. The sunset and sunrise is calculated or decided upon the upper edge of the sun disk. It's not the center of the sun. So there's a link for the spreadsheet here, and I hope everyone can test it and give me feedback. The accuracy is not perfectly like time and date, but here's the challenge. I just hope that anyone from the other side, from the flat earth side, can produce anything like that based on the geometry of a flat disk and a hovering sun at any altitude above that disk. If you get that with an accuracy of, say, plus minus 10 degrees, I'll be impressed. So that's all for now, and I don't think I need any proofs or any videos after this one. Okay, thank you for watching. Bye bye.